Thank you very much, Christina. So, please note the question mark at the end of the sentence. And the title is actually a pun on a somewhat famous book about epistemology history from a guy called Paul Feyerabend. I think he was from Austrian or German descent. It's mostly a pun, so don't take it too seriously. But yeah, I want to talk about my experience. I've been very cautious to replace my X handler with a blue sky handler. So, okay, so the agenda, what are we going to talk about? Of course, quick introduction. I will tell you about in which context I've been, sorry, maybe I'm just in front of this thing, so. Yeah.
No, it's better than.
It's back? Sorry, yeah, I was. Computers. I'm sorry, derailing the whole thing.
It's coming back?
Yes, sorry. So I will talk about the context and the experience and the experiments we did, because obviously I was not alone. Some findings and some analysis about this experience that I would like to share, and obviously takeaways and conclusion. Where do I speak from? So who I am, mentioned that I've been a dev, tech lead, architect, consultant, whatever, for 30 plus years. I also had a PhD in computer science 20 years ago. Starting to fade away, let's say. So, I mean, I just want to say that I've also had been involved in research, and I know, I sort of know how it works. I've been really, I view myself as a dedicated extreme programming practitioner, so I'm really interested in this, how this kind of methods. So I will avoid the A word, but I guess this is what we are talking about because it's been hijacked by managers. But I think extreme programming really embodies this kind of thing, the way I'm interested in working with a team in software. I view also myself as a cautious believer in formal methods. I've been practicing and developing in Haskell for 24 years. And I'm really, and by the way, do yourself a favor, learn Idris. This is awesome. Idris 2 is a really great language. So I'm really interested in this kind of stuff. I'm really interested as a practitioner. So I'm not going to teach you about separation logic. I'm kind of understand it, but I could explain it to my 15 years old daughter maybe, but that's all I can do. What I'm interested in is really to apply this kind of stuff to building software for the real world for users. And please take all what I say with a grain of salt. I've not seen every single method out there. My experience is limited to specific types of software, mostly backend stuff, distributed systems, in a financial-ish world. I have no experience with industry, for example, where formal methods probably mean something very different, and it probably has been applied for decades. So yeah, this is all caveats. If you get bored, I put a summary of what I'm going to say in the slide. So obviously, formal methods are not a silver bullet. Sorry if that disappoints you, but no, they aren't. On the other hand, I think they are really a useful tool to bring value for probably most software development teams out there. So I would say this is kind of more encouraging than the title would probably hint at. I think that if you're not Guillaume, and proving software correctness is out of reach for most of teams out there, at least that's what I've seen. And when I mean proving software correctness of software that run in production, in the network, in the distributed system, in the data center, whatever. And not because it's bad, just because it's extremely costly and intensive. We'll show that. On the other hand, I think that formal methods can be introduced incrementally in the software development lifecycle. I really think maybe one thing that I kind of realized, which might not be so obvious, is that formal methods can really help to grow and maintain what is called a ubiquitous language. So this kind of elusive concept from domain-driven design, where the idea is really to build a shared understanding of the thing we are building together with domain experts, with engineers, ops, all kind of people involved in software development. Yeah, so you can leave now if you want. You get the gist of it. If you want to stay, let's get into a bit more details. Why would you want to use formal methods? Yeah, and maybe one caveat which I didn't mention. When I speak about formal methods, I'm not talking about things which are, I'm not talking about B, for example. B is a formal method which prescribes everything you do for software from the onset to down to the compilation. I'm talking more about the use of, I would say, formal languages, more like, in the particular case I'm talking about, Idris2 or Agda or Coq or any kind of other thing which would be classified as formal method language. This is the definition which can be argued with. Well, first, yeah, fun, because it's cool, because you want to do a PhD in type theory, whatever. So that's the second part. Computer science, formal languages, formal systems are very useful, are used. We had a very good example in the previous talk. So yes, that's not what I'm talking about. Applied science, this is getting closer to what I'm going to focusing on. Applied science, like you are doing science and you are using a formal language and a formally and mechanically verifiable software and to back up your research. Typically, this would be writing a research paper and embedding or writing the machine checkable proofs for the thing you are talking about. This is close to what I've been working on. Obviously, software quality, you want to write and use formal methods to improve the quality of the software you build, which what I would call that makes the software right. You want the software to be correct, either by construction or by derivation or by thorough testing or just by wishful thinking. What I'm more interested in, and I think that's basically what I want to get at is, but you can also use it as for software design, like making the right software. Can we use more formal systems, formal languages, to make the right software, to not only make it right, but also to make the right thing? The context in which I did all those experiments is the context of the Cardano. Cardano, for those of you who don't know, and probably most of you don't know, is a blockchain or it's a cryptocurrency. The cryptocurrency is called ADA. Cardano is a blockchain. It's a large-scale, worldwide-scale network of things, distributed consensus. It's a globally distributed system, probably something like 3,000 plus block processing nodes and hundreds of developers and other nodes which are tapping into the system. So it's a large-scale system. Obviously, it's a system that moves money around, so security and safety is considered important. And within the company, so I worked at a company called Input-Output, IO, and there is already, there is an established tradition of using formal methods. I see some faces in the room that could vouch for that. So this is something that the company is already interested in. One last important thing is that research play a key role in the system and in the system development. So there are a lot of researchers which are working on blockchain technology, new ideas, and there are all researchers producing papers. So in this context, I was involved in a lot of quite a few R&D, what we could call R&D projects. I won't go over all of them, but they all had a kind of common theme. You get a more or less complex algorithm, could be some kind of consensus protocol, could be some kind of cryptography-related thing with proven properties. These algorithms are written by researchers. These researchers are cryptographic and security researchers. These are basically mathematicians. And the way they write these papers, they are using I would say, a heavy proof apparatus. So the proofs are massive. I don't understand them. So I just stick to the small thing that I want to implement. And then there is probably, in most of the papers that have been published by the company, you have 90% of the space which is devoted to the proofs, and they are complicated, and they are very technical. And to get to a working software requires the collaboration of people with diverse background and skills. So that's really the context. So I've been working with researchers, but also with people involved in the product down the road, people, formal method engineers, and so on. And we have strong and safety liveness requirements. So the main question, I mean, my job, basically, for about 4 years, was how do we turn, and the main question I was asked to answer, and I need to answer myself, is how do we turn the research papers into reliable working software? And by paper, I mean really paper, right? I mean, I printed quite a few of them, and it's like probably, I don't know, 30 centimeters thick on my desk. So it's heavy, right? So yeah, I'm summarizing this thing, and I think this diagram is actually kind of pointing at the issue is we have researchers, those researchers write research papers. These research papers are extremely complicated. They contain properties and proofs. On the other hand, you have developers like myself and the people I'm working with. We write software. How do we know that what we are writing is actually what the researchers wrote? Right. I mean, it's hard, right? So that's really basically what we were trying to do. I could spend hours telling you about the war stories and experiments we did and how we did it. But I will focus on just, and so the core idea is like, actually, in this particular context, researchers, they are domain experts. They are just domain experts. Like if you are in the bank, in investment banking, your domain experts will be traders or brokers. If you are in real estate, your domain experts will be real estate brokers. If you are in government, your experts will be lawyers, whatever, right? In the context I was working in, the researchers were the domain experts. So what did we do? And I would like to focus on one of the projects, the latest project I've been working on, and that's where we're really trying to start thinking a bit more within the context of so-called innovation frame, so just an R&D project. How can we kind of, I would say, structure this approach and find a way that we could replicate to other projects? We could turn into a method that other teams could be used, that we could generalize across the various projects, and how to get from research ideas to products. And when we speak of blockchain, product is an elusive concept, but so this was a small team. We had a researcher working with one of the researchers that wrote the paper. We had one from an engineer, and we had 2 architects/developers, including myself. And what we did was something like that. So we had really, I think what we're trying to do was really to find a way to put the formal specification. So that's where really the formal method part plays the biggest role. To put the formal specification at center. So, and to not only put it at the center, but also to put it within several feedback loops. So the idea is that we started with the researchers producing research, surprisingly. The good thing is that in this particular project, the research was not fully produced. Like we didn't start from a printed and published paper. We started from a polished idea, an algorithm, some proof, some properties, but it wasn't completely finished. And then we say, okay, fine, that's the best place to start with, because now we can really start working, and we can really start specifying very early in the process what the algorithm would be. In this particular case, this is doesn't matter for the discussion. So we started very early, earlier than usual, and say, okay, can we work together and work on the formal specification of this particular protocol? That's where, and then we started building this formal specification. But we also said, well, let's not wait for the formal specification to be finished. Let's work on the prototyping also, and let's build a prototype that would be different, that would be actually running. And the question was, how can we relate the formal specification to the prototype? And we wanted the prototype to also inform the research in some ways, saying perhaps there are findings in the wild, in the real world, that were not taken into account in the research. And actually they were. And the last part, which is more ideal, which we really never got to because, well, it's complicated, is that we also wanted product people to get involved into the loop, really to, we really wanted to get those people involved into the loop. So this is where you start to see this is a bit different from, I mean, the way we tried to approach the problem was really to think in terms of feedback loop and how the formal method specialist and the formal specification could be used at various stages and could be used within the feedback loop of the process. In terms of tools we use, so we work with several tools. I mentioned them just because you might find reference out there, and I will share with link at the end of the presentation. So one of the formal tools that we use was something called delta Q, which is a formalism that is used to model network performances at scale. So instead of the goal of delta Q is that instead of having to write a perfect network simulator and infer numbers from that, you would write a model which is just, to simplify, a graph of the various stages you would work with, and use probability distributions to compute the overall expected latency of what you are working on across the network. So it's a way to abstract and model a network. One of the main tools we used was Agda. So this was the formal specification language we used. We used Agda to HS, which is a tool to convert Agda to Haskell, which is different from the normal, I would say, the standard program extraction from Agda. The reason why it's different, and the reason why there are two different backends, not really backends, but two different ways to extract, that Agda to HS is really not a program extraction. It's really more a way to use Agda to make Agda proofs useful for Haskell programs. So it's more the other direction than what you would get with Agda. Just as an aside, other parts of the company were using the normal or the typical Agda code generator in a different context, but with somewhat similar principles. We also use something called Kuchik Dynamic, which is some Haskell code to generate the conformance test. More on that later. And we implemented prototypes using Haskell and Rust. So really the idea was to prove and to prove to ourselves, and also to generally to build something that would be independent of the implementation technology. So really to separate the different parts. Agda has a specification language. So how did we use it? Because this talk is about formal methods, so I'm focusing on that part. So the protocol was modeled using a small step semantic. So it's a distributed protocol across various nodes in the system that provides some guarantees and produces some certificates. And so you have a small step semantics, and we call that a relational model. So it's a relational model that says, well, I have a state, some action happens, what state do I have? So that's typically a relation between states. And the formalization effort itself initially took inspiration from some previous work. I put the link of the paper, which is called Formalizing Nakamoto-Style Proof of Stake in Coq. And the idea was to leverage previous work that was already done in terms of what kind of, so how would you go to model and formalize a distributed protocol like that, decentralized and distributed protocol? What kind of proof technique would you need to use in order to get the guarantees you want to get at? So we really took heavy inspiration from this paper, at least initially. It turned out that this was mostly a dead end, but more on that later. And we put a heavy emphasis, and that's the part of the feedback loop, that the importance of the feedback loops that I showed earlier, on producing a readable specification. By readable specification, I mean that we tried, and I think we achieved, we managed to really separate what's relevant to the description and the definition and the specification of the protocol itself from what are the noise, would say Guillaume, about the thing that, well, you care and you need because you need to, this is your formalism requires it, but it's not really important it's not really making the point. So much so that, and we leveraged the literate capabilities of EGDA, nothing super fancy, but this was really an important part of the project to really communicate very early and to use that as a way, as a communication hub or as a way to talk about what we were doing and how we were formalizing things. I think that the readability part is very important, and it's very important to communicate in the various, with the various parties involved. Another part, and then another part where the form method was involved, which is like the downstream part. So how do you relate the specification to the implementation was we used EGDA as a way to generate and generate test model and test traces against an arbitrary implementation. I won't go too much into the details of this. I talked about this last year, actually. But the idea was that we have our relational specification on one side, and with some proofs, and we have our so-called executable specification. So when you have a relation, it's not productive, right? You know that two states are related, but how do you get from one state to the other? You need to construct a new state, and it's not exactly the same thing. So we had another specification, which is the state machine, and the tricky part and the interesting part was, well, how do you relate the two? Well, so how do you relate to the program, and how do you relate to the specification? To relate to the specification, we needed to write a soundness proof, proving that whatever we did there was actually correct with respect to the relational specification. And downstream, we needed to build, we needed to use that model in the Haskell world or in the Rust world to generate traces and use, in this case, QuickCheck to test our program. Okay, so that's the general context. I'm going quick because I could spend hours, like I said. There are references at the end of the talk where you will really get, if you can be overwhelmed by details if you want. There are a lot of them. We wrote a journal of all this stuff. So there are reports, there is the logs, there are codes, whatever. What are the outcomes? Okay, so what went well? What went well, and that was really, is that from this effort emerged a better standard. So one of the goal in one of the process we have in the calendar world is to produce standards like RFCs for the blockchain. And this protocol, so PERAS, was the first to produce an RFC which contained an EGDA specification. And we were able to do so because the EGDA specification, we took somewhat great care to make it readable. In a sense, like readable, but not readable only by tag theorists, readable by, me, normal engineers. And that's what's really important. So, yeah, obviously the import part is not the most interesting one, but yeah, I should have. But yeah, by the way, this is a link, so you can have a look by yourself and judge whether or not we achieved that. I think I have anecdotal evidences that this is actually the case because we had a lot of engagement from the community on this standard, people reacting to it, discussing, pinpointing issues, finding errors, whatever. So this was really good, and I think we achieved part of our goal, which was to use the formal specification as a communication tool. Another thing, like we really get to this putting putting a formalism, which was, I mean, practically speaking, writing proofs is hard, but specifying the types and the shape of the system and embedding already some assumption and some security aspects is relatively easy and much faster than implementing the thing actually. And so thanks to the specification, we really had a very faster feedback loop, and we were able to report back to the researchers shortcomings or findings we had that nothing super earth-shaking, but well, actually no. There was one occurrence where the delta Q model we built actually made the researchers realize that their initial proposition couldn't fly. It was impossible because of the requirements of the network. It was too heavy, so they had to rework this. It didn't jeopardize the protocol itself, but what was interesting even more is that by having a formal model and having a prototyping effort and relating the two through tests, through a somewhat formal process, is that we were able to find bugs in both directions. Like the specification itself, it's written by a human being so far, so it can have bugs. And by having these two kind of, it's like it's like having two teams build the same thing and compare to really get sure that what you are building the right thing. So this was also an interesting insight. And having a small formal model which was really self-contained and really addressed most of the points of the system was really proved really useful to bootstrap the development process, which is now ongoing. And the last thing is that it was a surprise of sorts, is that we didn't implement it really, but we really get to the point where we say we need that. So we need actually a research DSL. And so what I show you here, this slide, it's a screenshot of a Word document. Our researchers, like probably all security and cryptography researchers, they are not programmers. They are mathematicians. They write proof with pen and paper, or with Google Doc, or with LaTeX. Yes, I know this is a shock, but this is what they wrote. Turns out that if you read carefully the 3 or 4 pages Google Doc document that they wrote, you realize that some variables are not even defined, so you don't even know what. We sat together and say, what if we wrote this, right? This is ACDA code that's machine checkable, that compiles, type checks at least, doesn't produce anything useful because there is no semantics, but at least it type checks. So there was this idea that, unfortunately, we didn't get to the point of generalizing it, but that we planted the seed of saying, well, a formal language like ACDA could be great to build a research-focused DSL. And that's really, and this research-focused DSL would be something that maybe the researchers would write, but more likely the engineers would write with them, but they would be able to put that in the paper, use a LaTeX generation from, and you would have, even already in the paper, you would have the seed of the whole formal process. That's the good part. What could be improved? These are silos. So the reality is that formal methods and formal languages are different, right? I mean, this is a different set of skills. So integrating them in the day-to-day development process is not straightforward. formal method engineering is not yet widespread. It's not yet widespread in trainings, in universities, in the experience of developers you hire from anywhere. So, well, it's different, right? It's pretty new, and even people who had a training in formal logic, like all engineers. I mean, there is a gap, and the gap is also the fact that it's a whole new ecosystem. If you have to write Idris code or IDA code or Coq code, you have to learn, well, the ID, writing the code, the syntax, the semantics, the standard library, because obviously you are not going to reinvent set theory from scratch. Well, some people did it, but creating silos is a slippery slope, which leads to something I call the DBA or ivory tower situation. So the DBA situation is I would say the benevolent manifestation. Like you have a specialist, and this person knows the thing inside and out, and they have a very specialized knowledge, and they become the bottleneck because everything has to go through them because they are the only one who know it. If your specification and formal specification is at the center of your process, this is what you get. This is what you end up with. The ivory tower is the less, I would say, benevolent manifestation. It's like people being annoying and insisting on having everything done right in Agda with all the proof written before anything can be done in software, and everything has to go through them. We didn't have that. That's unfortunately, but the DBA effect was already something that even in the small team of 3 people, was already something, and 3 people with experience and interest in this kind of stuff. So this is something we experience, and we experience in other parts of the system. This is not very charitable for Coq, but we had the same in Agda. You can't read it, right? I can't either because this is a proof. This is a fragment of the proof of one property, or probably one lemma, from the paper I referred earlier about the Nakamoto proof of stake thing. So this is a Coq proof written written by someone, I guess, because there are comments. My question is, how do you maintain that? Right, you come back 6 months later. Okay, yeah, you have a compiler, you have to figure these are very powerful, but putting the person, if the person leaves, right, the whole question of maintenance, the whole question of keeping the formal specification and maintaining them over time is really key to me. And when it comes to tool and process, I won't go too long into it, but I think, well, it's not an insult, or it's not, insulting anyone to say that formal methods being not so widespread, the tooling is not on par with what we have in industrial language. And even, that's just a fact. And sometimes the needs of research and industry are not aligned. They are somehow conflicting. So what development don't always go into things that would be useful for developers. And last but not least, the landscape is very fragmented. If you have to choose which one, right? Well, most likely you have one person in your company or environment that knows X, and then, well, you go for X. Okay, some conclusions. Some philosophical detours. Those detours will lead us a bit too far astray, so I will just shortcut. Some of the ideas, I mean, the idea of this talk came to me by reading not only Against Method, but also this book from Billy von Kuhn, which is called Discussion of the Method, and in which, so this guy is a nuclear engineer, something which has a strong background in mathematics, and it talks about what engineering is, and his conclusion is that engineering is basically 100% heuristics. And heuristics together, a set of heuristics is a state of the art, and it's just a bunch of things that you are doing that you know at some point in time that the team is convinced that they need to do something, and that that's the state of the art, basically the best they can do at some point in time. Which basically means that, yeah, formal methods are good if they bring value to your system. If they are not good in and of themselves, I would say. And then this one, you can read it. This was in preparation for the talk. It's even harsher because it takes what this guy said, but at the level of really science, saying, yeah, you think about the scientific method, but there is no scientific method actually in and he has proofs about it, or at least facts to back up his proof. So some takeaways. My first takeaway is if you want to use, if you have the people, and the key is of course having the people with an interest, some background in formalism, even not much, right? But some background. Of course, we had researchers and cryptographers, but my experience is that even working in investment in banks and a lot of people they have a lot of domain experts, especially in software. They have they need to formalize things. So engaging with domain experts as early as possible is a great way to start very early with a small seed that you can then grow. I also think that what we did, so model-based testing, using the model that you build as formalization as a tool to test your actual implementation, is a great way to introduce formal language and methods in an environment. In general, testing is a great way. We all know that, well, if you write your test in Haskell, nobody will care, even if the company is Java-based, because, well, it's not so important. But then you are sneaking in Haskell. Here, it's just the same, but at another level. I would say start small, but that's kind of obvious, right? Focusing on some part of the system, not trying to formalize everything. That's also kind of obvious. One thing which I think is very important, but maybe often overlooked, is the fact that you want to ensure the collective common ownership, even of the formal specification part. This is hard and tricky because you need training, you need pairing, potentially mobbing with people, and a lot of mentoring, which means that, well, this slows the people down. And there is always a tension between, you have formal method specialists, are they producing formal specifications, or are they training others? Hard choice, right? No, it's not a hard choice. You will go for producing stuff, which is probably an error. Yeah, the last one, select one tool and stick to it. That's what kind of I/O ended up doing. I've heard that it's not the case anymore, but whatever. And last but not least, do not put proofs on the critical path of the software. Like writing proofs, using the formal language and the system as a theorem prover to write proof of the properties is important. And obviously, that's the whole point of it. I mean, that's part of the point of it. But if you put that on the critical path, then you are doomed because it will take ages. And then a sentence list to the formal method community. So please, tooling and developer experience. That's what we need, really, to bring that to the world. I would say lower the barrier of entry also through practical training material. What I mean by practical training material is like this kind of, I could potentially share that, but PLFA is great, but it's not very practical, and that's the kind of thing, right? Trying to find good examples where we can really say, oh yeah, in my context, I could do that. Potentially, and then probably nobody can do anything about that because it's tied to research, but consolidating the formal method language and method landscape would be great. I guess that's all I have. This is a paper. This is actually some work from a paper that we published with. So James Chapman is head of formal method at I/O, and Paulina Vinogradova, she's a formal method engineer there. There is a website and code repository where you will find all this stuff and much more. And I would like to thank you. So thank you, my colleagues at IOG. This was really a fun ride. I would like to thank PopConf organizers. A lot of people who helped me rehearse and review this talk and hopefully improving it so you don't have the raw version. My friend Christophe for the inspiration, and of course, thanking you for coming to this talk.
Thank you very much. And again, we are perfectly in time, so we have now time for questions. And we're starting back, there.
Okay, so on one of the first slides, you showed that problem was how do you make sure that the code, the final program, and the research paper match. Now you disassembled that into two steps, namely the formal method in between. So I think we can be all convinced that making the program and the formal specification match is not that much of a problem, because there's proof, program extraction, and so on. But how did you make sure that the formal specification and the research paper matched?
So I would argue that the first part is not so obvious. Program extraction in practice, I would say I'm not convinced, to be honest. I'm convinced by the Idris approach, which is like more constructing program and compiling to a performance comparator. I have not yet seen program extraction to produce particularly I mean, I've not, in my experience, the program extraction part has not produced something that we can put in production.
You can use an oracle.
Huh?
You can use it as an oracle for your running condition.
So that's what we do. So we relate the two. The conformance testing is a way to relate the two. To relate the proof, the paper and the specification. This is this is ongoing work in progress, and the idea is to add this research DSL where the researchers are not working on something which is, their own LaTeX equations, whatever, or proof of paper, is to write on is to describe the algorithm and whatever they are working on using already a formal language, and this formal language will be part of the whole chain. This is a bit not yet. I mean, I think we are not far from it, given the researchers we have in this context. Unfortunately, I left the company, so. But this is a different problem. But I think this is something important, even if you don't write all the proofs that the researchers write using this system or using the formal language you have. At least you already have the type. You have the types right. You have mostly the types and the overall structure right. And you are talking about the same things and potentially describing things like when you are in the protocol and describing a small step semantic, even if you don't write the proof that the properties are right, writing them, having a formal specification of the small step semantic is something you can put in your paper, which expresses your algorithm.
Yeah, but very concretely, in your project, somebody wrote the actor code and you went to the researcher and said, hey, look, is that what you meant?
Yeah, exactly. That's what's the problem. That's the problem we're trying to solve later with the. That's the problem we're trying to solve by showing them and writing with them a formal representation of what they wrote in their paper. And it's not done yet. I mean, that's what I said, right? It's a hard part, but it's something that I think. That's why I'm relating that to this idea of having a ubiquitous language from domain-driven design, which is also very elusive. In practice, domain experts don't want to talk to you. Really, right? And a lot of that, and to be fair, a lot of developers don't want to talk to domain experts. But I think if we don't, this is the hard part. If we don't do it, we are doomed to keep, having this kind of not building the right thing. We can build the thing right, but we are not building the right thing. The point I'm trying to make is that this is the hard part we need to scale up. And I'm not saying we did achieve or succeeded. We did a step that direction, just to be very clear.
And I'm extremely curious about your concordance proof, because naively, I was imagining that, okay, I have a very strong definition and very strong types.
The soundness proof, you mean?
Yeah, soundness proof.
Yeah.
Strong concordance. And I go to a scale which is a very dynamic language, which is a very complicated semantic. And I can say that, okay, what I'm unsure is probably yes by the generator I will use, because in my generator for the ACTA part I'm more strict about potential value, because I know the Philip set and probably not in the scale work.
Yeah, it's not perfect. Yeah, that's test. Yeah, but the soundness proof at least tells you that the model you use to generate your tests is sound with the specification you wrote, which expresses the whole word that you are supposed to describe. again, it's imperfect. I'm willing to agree, and but I'm trying to be an engineer, so I'm trying to do trade-offs. And my trade-off here is speed versus correctness, and I think this is a way. In my view, this path is a way to get more correctness faster than what you would do with different either you would get less correctness because then you have the two things in parallel. I mean, we did that once. In one project, we had that. We took the paper and we implemented the paper by reading the paper and talking to researchers. And probably, I don't know, 1 year down the road say, is this actually the same algorithm that's in the paper? It turns out no. And turned out there was a bug, right? So we already discussing and trying to put a bit more formalization, mechanization in this path is already better than none. That's what I'm saying. I'm not saying a bit more. Yeah, taking 45 minutes of your life to just say that, maybe it's too much. But